Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing on into section 8.2, doing a quick summary of surface area, and then looking at an example that'll sort of run us through all of the geometric ideas that we've covered in our class using definite integration. So we'll take a look at an example that'll review how to get volumes of solids of revolution, areas under curves or areas of regions, as well as our new concepts of arc length and surface area. Before we do that though, let's quickly summarize what we discussed from the previous video concerning surface area of surfaces of revolution. So, if you recall, we had two situations that we discussed. First, we discussed surface area around the x-axis. Remember here, the sort of visualization is that we have some curve floating here. We said that you can think about that curve as either being from A to B in terms of x or from C to D in terms of y, and then we're imagining revolving that around the x-axis and giving us sort of a mirror image there, and then we're building some sort of three-dimensional shape like that. And then the idea was that the way we actually sort of measure that is by taking a little piece, if we sort of cut that sort of little piece here, and if we look at revolving that individual piece, so that looks a little ugly there, that individual piece, then how did we actually understand that piece? Well, we said that what was going to be sort of important in that is understanding that radius component there, and then also making sure that we understand the component along here, which once we straightened out, we saw that that was going to be the arc length there. So remember that in general, we came up with a sort of general formula for the surface area in this situation, which was going to be 2 pi times the radius times that height. And remember, in this case, the radius would be that y component, so 2 pi y, and then that height component, because the sort of cylindrical piece that we're making is on its side here, would be the arc length. Then we broke this general formula down into two situations depending on which variable of integration we want to use. If we want to work with respect to x, well, then we would integrate from a to b because those are our x bounds. 2 pi f of x, so we'd have to use the function because we can't use y, so we'd have to replace the y with f of x. And then for the arc length, we would use the x definition of arc length, which is the square root 1 plus dy dx squared, and then integrated dx. If we choose to work with respect to y, then our bounds of integration would be c to d, so we'd be working from here to here. 2 pi, we would not need to put a function, we could just leave it as the variable y, because that's our variable of integration. And then for arc length, we would use the y definition of arc length, 1 plus dx dy, so the derivative of x with respect to y squared dy. So remember, both of these are just versions of this general formula. This one is for using if you want to work dx, this one if you want to work dy. All right. We did learn another situation, though, which is also how to deal with revolving around the y-axis. So we had a second situation, which is the surface area around the y-axis. So here, our visualization is a little bit different. Now we're sort of imagining we have some axes, again, some curve. Now we're revolving around this, so our mirror image is sort of over here, and we're constructing some sort of 3D shape. Once again, the sort of idea behind this was if we take a look at an individual piece, then if we follow that piece out to here and here, same thing here and here, well, then this was the sort of shape that we were using to build those pieces. So this time the cylinder the cylindrical shape was sort of in standing upright like we would expect. This time this distance here was going to be the radius, and this piece here, well, that's going to be your height, which is going to be that arc length once we smoothed it out. That meant the general formula this time was 2 pi x times the arc length, because this time that radius is in the horizontal direction, so it's the x distance. Then we took that general formula and broke it down into two specific situations. If you want to work with respect to x, well, then if we have the bounds of our interval here being from a to b, And if we imagine here C to D, well, then you would integrate from A to B, 2 pi, you'd leave this as x because you're working with respect to x, and you would use the x definition of arc length, which would be the square root 1 plus dy dx squared, and then integrated with respect to x, or dx. If you want to work with respect to y, well, then you'd have the integral from c to d, so you'd use these bounds. 2 pi, you can't leave this as x because you want to work dy, so we'd replace x with a function of y, so treating x as a function of y. And then we would use the y definition of arc length, square root 1 plus dx dy squared, and then integrated with respect to y. So the reason I wanted to summarize here is because we want to make sure that we understand that we have, in this sort of thing, two different situations: what happens when you revolve around the x-axis and y-axis, and then in each situation we understand how to integrate both with respect to x and with respect to y. Remember, these are going to always yield the same answer, those two different formulas, because they're just two different versions of the same overall thing. Now, of course, revolving around the y-axis and revolving around the x-axis, those are very different. As you can see visually, this gives a very different shape than the one we're looking at here. So we have to make sure we understand we have two different situations: what happens when we revolve around the x, what happens when we revolve around the y, and in each situation we have two different formulas depending on whether or not we want to build an integral with respect to x or an integral with respect to y. To help us sort of get a little bit more practice with this and to review some of the earlier geometric ideas that we investigated using definite integrals, well, let's go ahead and take a look at sort of one large example where we're going to take a look using the same curve and in the same bounds to analyze all the different geometric aspects that we've learned about. So that'll be areas, arc length, surface areas, and volumes. So let's go ahead and take a look at that. So for this entire thing, we're going to use the curve y equals tangent x. And we're going to go through a series of questions. Looks like we got 1, 2, 3, 4, 5, 6, 7, 8, 9 different things. We're going to do some areas here and here, some volumes here, here, and here, the arc length, and some surface areas. And for every one of these, we are also going to make sure that we write down integrals. We're not going to evaluate them. We're just going to write them down. And we're going to write two integrals for every one of these geometric quantities, one with respect to x and one with respect to y. So at the end of this, we should have 18 different integrals that we've constructed so that we can make sure that we're completely comfortable with using definite integrals to understand geometric quantities. So let's go ahead and get started. So we'll give ourselves a blank page, and the first one that we're going to do is we're going to take a look at the curve y equals tangent x. We want the area under this curve and above the x-axis from x equals 0 to x equals pi over 4. So let's give ourselves, since we're going to be using the same region over and over again, might as well draw a diagram at the beginning, then we can be much faster in the sort of future. So we know that we're going to be going from x equals 0 to pi over 4. And of course, at pi over 4, tangent is going to be at 1. So the section of our sort of curve that we're looking at is something that looks like that. Of course, tangent overall is going to go up, and then of course look something like that, where you have a vertical asymptote at pi over 2 and another vertical asymptote at negative pi over 2. But we're just interested in this little section. Now, we're also looking at an area, so we need to define the region, not just the curve. We want the area under this curve and above the x-axis. So the area we're going to be interested in is going to be this blue shaded region. Okay, so let's write down some integrals there. So we'll just go ahead and do the dx sort of first. So if we want to do an area here, working dx, well, we're going to be filling this in with vertical lines. You can see that the bounds for that integral are going to be the integral from 0 to pi over 4, because we're working dx. And then it's just measuring from the curve down to the x-axis. So it's going to be integral 0 to pi over 4, tan x dx. So nice and easy there, right? Just the integral from 0 to pi over 4, tan x dx. What if we want to work dy? Well, we should probably then go ahead and label this. We should make sure that we realize that this point right here is pi over 4 comma 1. Also keep in mind that if we want to work with respect to y, if we have y equals tan x, we're going to have to think about x as arctan of y. So how would we sort of get this area then? Well, when you're working dy, you'd be sort of filling this in with horizontal lines. Notice my horizontal lines are between my curve and pi over 4. So the area here would be the integral. Bounds would be from 0 up to 1. And we'd be measuring, if we were looking this way, well, the pi over 4 is further and the arctangent is closer. So it'd be pi over 4 minus arctan of y dy. If you want, you can do these integrals on your own. This one's, of course, not hard to do. This one's a little bit messier, but you can actually deal with integrating the arctangent using an integration by parts. If you go ahead and do that, these will, of course, yield the exact same value because both of these measure that blue area there. All right, so we've accomplished our first one, which is to write down two separate integrals, one with respect to x, one with respect to y, that both measure the area under this curve and above the x-axis from x equals 0 to x equals pi over 4. All right, let's try something else with this. So now we want to get the volume of the solid created by revolving the area under this curve and above the x-axis from x equals 0 to x equals pi over 4. So same region around the x-axis. So let's go ahead and do that. We can sort of quickly draw that now. There's going to be our curve. Okay, pi over 4. We know up here, pi over 4, comma 1. And then, of course, this is 1. And now we're going around the x-axis. So we're revolving this way. And we're taking this area here. The sort of mirror image that we would get is going to look something like that. That's probably a little far. There we go. And then, of course, what we're actually going to be building is some sort of shape like that. And, of course, it'll actually come to a point right there. So how can we do this? Well, we got to remember that if we have a horizontal axis of revolution, which is what we do, then our dis and washer method will be dx, and our shell method will be dy. So let's go ahead and take a look at that. We'll do the dis and washer method because we wanted to just do dx sort of always first to stay consistent. Remember that with dis and washers, what you do is you draw from your axis to your region. You draw perpendicular. So if we draw from our axis, we get something that looks like that. And that would give us our typical disk right there. You'll notice that our region is adjacent to the axis of revolution. So when we do this, we're not going to actually have washers. We are just going to be back to having a straight disk here. So what is that going to look like then? Well, our volume is going to be the integral. We can make those selections from 0 to pi over 4. Then we'd have pi, and then we'd have to have our radius, which is going to be our function. So tan x squared dx. The inner radius, if you want to think about it that way, is 0. So you could put minus pi times 0 squared. You could also think about the tangent as tan x minus 0 if you want to include the axis of revolution. But there we go. There's our volume there. And that was using dis and washers right there. Oh, let's circle the whole thing. All right, what would shells look like? Well, shells we'd be drawing parallel to our axis. So we'd be looking at something that looks like that, revolving down to here, and creating our sort of cylindrical shell like that. So the shells are on their side. So in that case, what we would have is we'd have the volume. Those shell selections could be anywhere from 0 to 1. Then 2 pi. The radius, well, the radius is going to be that. It's going to be based on our choice of y value. So remember that in cylindrical shells, it's always just the variable and the axis of revolution. So here it would be 2 pi y. And then, of course, the height, which is on its side here, is going to be measuring from our function 2 pi over 4. Of course, remember, we got to treat that function in terms of y, so arctangent of y. So our height here would be that pi over 4 minus arctan of y dy. So there we go. There's two volume expressions. One using dis and washers, which allowed us to work dx, and one that used the cylindrical shell method so that we could work dy. All right, let's go ahead and get to our next one. Also a little bit of review. We want to do the volume of the solid created by revolving the area under this curve and above the x-axis from x equals 0 to x equals pi over 4 around the y-axis. So same region, but different axis of revolution. So let's go ahead and take a look at that. So for C here, we'll draw our curve. Same thing, we sort of know the key features here. There we go. It's a little off. There we go. So we know that this is pi over 4. This is pi over 4 comma 1. This is 1 here. This time we're revolving around this. So our mirror image would look something like that. And we're building that sort of shape here. Okay. So, and same thing, we should fill in our region. Because remember, whenever you're doing volumes, you need to not only define the curve, but you need to define the region. It's the fact that we have an entire area that's making an actual solid that has volume. Later on, when we get to arc lengths and surface areas, especially surface areas, we don't need to worry about the region. We're just going to be interested in the curve. But for volumes, you need to know the area that you're revolving, not just the curve you're revolving. Okay, so in this case, because we have a vertical axis of revolution, so we have a vertical axis, which tells us that dis and washers is going to be done dy, and shells is going to be done dx. So let's again go ahead and start with dx, so we'll use the shell method first. So again, we'll do that sort of in red here. So shells, you always draw parallel to your axis inside your region. So a typical shell would look something like that. It would get revolved to over here, and the shells would be standing upright like that. All right, so that means the volume would be the integral. Of course, the bounds still from 0 to pi over 4, because we're working with respect to x. Then 2 pi. Radius here, well, it's going to be the distance from there to there, which is, of course, just based on your choice of x. So we'd have 2 pi x, or you could say x minus 0. And then, of course, the height, well, it's just up to your curve, so it'd be tangent x dx. So there's the volume for going around the y-axis with respect to x. Let's come up with an equivalent one using dis and washers. So, dis and washers always go ahead and draw perpendicular to your axis. So, if we draw a typical disc or washer, there we are. We hit the region once. Notice that that's going to give us our inner radius. So this is going to actually be a washer. And then we'd hit it again, and that would give us our outer radius. So we are going to actually have an inner and outer radius when we do this dis and washers here. So the volume is going to be the integral. We can do this anywhere from 0 to 1 because we're working dy. Pi. What is the outer radius? Well, it's measuring from here to here. That's from the axis, which is 0, to pi over 4. So it's going to be pi over 4, technically minus 0, and then squared. And then minus pi times, well, the distance from your axis to your curve, which is, of course, arctangent, because we're working with respect to y. So arctangent of y squared dy. So there we go. There's our expression dx. There's our expression dy here. For the volume, when we take this region under tangent from 0 to pi over 4 and revolve it around the vertical axis or the y-axis. Okay, so I wanted to do these three first because they're all related to one another. You'll notice that we first understood the area, and then we looked at the resulting volume when we revolved around the horizontal or vertical axes. Notice that everything sort of lines up here because since we understood the areas here, things like the bounds and even the structure stayed the same when we did the volumes here. And this is really to just reinforce to you guys that volumes are dependent on the region or the area. So if you can understand the area back here, then it definitely helps you understand the volumes when you revolve that area. Okay, let's try a couple more. So we'll give ourselves another page. Now we're going to do a different area, so a different region. Now we're going to be interested in the area to the left of this curve and to the right of the y-axis from y equals 0 to y equals 1. So different region. So let's go ahead and take a look at what this is going to look like. So if we draw this region out, so we've got the same tangent curve, something that looks like that, but we're going from y equals 0 to y equals 1. So there's y equals 1. We know that that's still going to hit at pi over 4. So we're still looking at the same piece of curve, but instead of looking at the area here, we're now looking at the area here. So we've got this stuff here, and we're now going to be interested in this stuff in here. Then again, we can still label this as pi over 4 comma 1. And of course, we still have y equals tangent x, or if you prefer, if we need to work with respect to y, x equals arctangent of y. Okay, so let's go ahead and get some area formulas for this to start with. If we're working dx, then we're filling this thing with these sort of vertical lines like this. Now, you'll notice that those vertical lines go from 1, and then they reach down to the curve. If you're looking from the x-axis and you're looking up, the curve is on bottom and the 1 is on top. So this area should be the integral from 0 to pi over 4, 1 minus tangent x dx. So this 1 minus tangent x measures the distance between 1 and the curve, and of course we do that from 0 to pi over 4. If you want to work dy, then an equivalent integral would be the integral from 0 to 1. You'd be using horizontal lines stretching from the axis to the curve, so it would be just the integral from 0 to 1, arctangent y dy. And there we go. So two equivalent integrals, one with respect to x, one with respect to y, for that area there. Now let's go ahead and revolve that area around some axes. So if we go back, what we're going to do is we're going to take that same area and revolve it around the x-axis, so around the horizontal axis. So for E, we'll take the same sort of region here. Okay, so same sort of piece. Right there, that's at 1, that's at pi over 4 comma 1, that's at pi over 4. And once again, we're taking this area here, and now we're going to revolve that around the x-axis. So our sort of mirror image is going to look something like that. And we're building this sort of shape there. There we go. So if we want to do this, well, we have a horizontal axis of revolution, which means that dis and washers is going to be dx and shells is going to be dy. So we always want to sort of start with doing the dx. So let's go ahead and we'll keep our colors consistent. I think we were always doing dis and washers in green. Yep. So dis and washers again, draw perpendicular from your axis to your region. So there we go. There's where we hit the region. So that's going to give us an inner radius. And then that's where we exit the region. That's going to give us an outer radius. So when we go ahead and do our dis and washers, they are really going to be washers. So our volume here is still going to be the integral from 0 to pi over 4, because we could do this anywhere from x equals 0 to x equals pi over 4. Then pi, outer radius, is going to be stretching from that 1 to our axis, so 1 minus 0, so just pi 1 squared, minus pi. The inner radius is going to be from our function to the axis. Our function is tangent of x if we're working with respect to x. So just tan x squared dx. So there's our volume expression there with respect to x. If we decided to do this using shells so that we could work dy, shells you always draw parallel to your axis. So there we go. There's a typical piece that would end up down here, down there. Of course, the shell would be on its side like that. But you can sort of see what that would look like. So that volume then, well, those choices could be from 0 to 1. So we'd have the integral 0 to 1. 2 pi. The radius, which would be this, is your choice of y value. So you'd have 2 pi y. And then, of course, the height, even though it's on its side, would be out to our function. And, of course, remember our function is arctangent. So we'd have arctan of y dy. So there we go. There's two equivalent integrals, one with respect to x, one with respect to y. For the volume, if we take this region to the left of our curve and to the right of the y-axis and revolve it around the horizontal x-axis. Okay, one last volume. Let's go ahead and do this around the vertical axis. So here, and then we'll be ready to take a look at some of the newer things. So same region, something that looks like that. And of course that point right there, that's pi over 4, 1. And pi over 4, and we know that that's 1. And we're taking this area here. This time we're revolving around the vertical axis. So our mirror image would look something like that. And we're going to be building this sort of shape. So it's sort of a bowl shape that comes to an actual point at the bottom here. So I guess it would tip over if you actually had it, if you actually built this shape, but that's okay. So let's do the same sort of approach. We've got a vertical axis of revolution. That means discs and washers will be dy, where shells will be dx. So we want to start with doing a dx, so we'll go ahead and do the shells portion. So remember, shells, you want to draw parallel to your axis. So a typical shell is going to look something like that. Revolve that around, going to do that. And there's going to be your sort of typical shell. So that means your volume is going to be the integral 0 to pi over 4, 2 pi. What's going to be your radius? Well, it's going to be your choice of that x value, so just 2 pi x. And then the function, well, or the height, well, it's going to be based on measuring from 1 to your function. So it looks like it should be 1 minus tangent x dx. So there we go. And of course that height component is measuring right here where the 1 is above our curve. Okay. If we go ahead and we take a look at doing this dy, so using discs and washers, well, for discs and washers, we want to go ahead and draw perpendicular to our axis inside our region. So we'd be drawing this way. Notice we really only hit the region once. So that means we only have a disk. There is no inner radius, or you can think about the inner radius being 0. So that means our volume is going to be the integral from 0 to 1 pi. That radius is measuring out to our function. We're working with respect to y. So we think arctangent of y squared dy. No inner radius because the inner radius is really just a 0 there. Okay, once again, hopefully you guys can sort of see that if you understand the areas here, they directly tell you about the resulting volumes, because remember, these volumes are defined not just by the curve, but by the region you're revolving. All right, now let's start talking about some of the newer things with arc length and surface area. So if we go back, we're going to take a look at G, which notice this says the arc length of this curve from x equals 0 to x equals pi over 4. No need to define a region because we're just talking about the length of the curve. So let's go ahead and look at that. So give ourselves another page here. I think we are on part G. Yep, call this G at this point. So we don't really need the diagram, but I'll just go ahead and draw it. So there's pi over 4, and there's 1. So we have this piece of our curve here, and we're going to be measuring the distance along that curve. And again, remember, we have y equals tan x, or we can think x equals arctan of y. Let's get some derivatives too, which we will need. Dy dx is going to be secant squared x. And if we go ahead and do the other derivative too, because we're going to do an integral with respect to x and one with respect to y, dx dy is 1 over 1 plus y squared. So we will need each of those. So let's come up with some arc length formulas. The arc length with respect to x would be the integral from 0 to pi over 4. Again, just using the x bounds. Then we'd have the square root 1 plus the derivative of y with respect to x, which is secant squared x. And then we'd square that derivative, dx. So eventually we'd have to deal with 1 plus secant to the 4th square rooted. Very nasty integral, but again, we're just interested in setting it up. All right, if we decided to work with respect to y, the bounds of integration would be 0 to 1, because we'd be imagining working from there to there. Then square root 1 plus, now we use this derivative, so 1 over 1 plus y squared, and then all of that squared. And then we'd integrate with respect to y. So there we go. There would be two equivalent integrals, one with respect to x, one with respect to y, that would measure the distance from here to here along this curve, which of course we know would be a longer distance than just the straight line distance between the point 0, 0 and the point pi over 4, 1. So we're measuring the distance along that tangent curve. All right, let's save these on the same page and we'll look at some surface areas here. So now for h, we're going to go ahead and look at the surface area if we revolve this thing around the x-axis. Now again, notice we are just saying revolving this curve. We don't care about the region because we're just looking at the outside or the surface of the solid, not the actual volume. It doesn't even need to be a solid. We're just looking at the surface area outside. So if we go ahead and do that, draw our curve. Okay, there's pi over 4, there's 1. Now we're revolving around the x-axis, so we're getting sort of something that looks like that. So the surface area we're looking at is the stuff that is spun around outside there. So let's go ahead and take a look at that. Since we have surface area around the x-axis, remember the general formula is going to be 2 pi. The radius is going to be measuring that vertical distance, so 2 pi y times the arc length. So if we work with respect to x, we'd have 0 to pi over 4, then 2 pi. Then in terms of y, well, we can't use y because we want to work with respect to x, so we'd replace it with the function, which is tan x. And then for the arc length, we would use this x-based arc length expression. So 1 plus secant squared x squared dx. So there's our surface area for going around the x-axis if we want to work with respect to x. If we chose to work with respect to y, the surface area could be written as the integral 0 to 1, 2 pi. We could just leave this as y since we're working with respect to y, and then square root. In here, we'd want to use this arc length, so 1 plus 1 over 1 plus y squared, all of that squared, dy. Again, both of these would evaluate out to the same thing. They're both measuring the same surface area, but one is with respect to x, one is with respect to y. All right, last one. Let's go ahead and take this curve and revolve it around the vertical axis and get the surface area. So there we go. 4. There's our curve. Now we're revolving this way. So we're making this sort of shape, this weird sort of tippy bowl shape again. Surface area in general around the y-axis. Well, the surface area here is going to be the integral 2 pi. Now the radius is always going to be measuring this way, which is the horizontal distance. So 2 pi x times the arc length. If we wanted to work with respect to x, our surface area would be the integral from 0 to pi over 4, 2 pi. This x we could just leave as x because we're working with respect to x, so 2 pi x, and then square root. Well, we would use this expression, the arc length in terms of x, so 1 plus secant squared x squared dx. And there we go. There's the surface area for this shape with respect to x. Finally, if we did this with respect to y, we'd have the integral from 0 to 1, 2 pi. We would not be able to leave this as an x, so we'd have to replace x with the function, which would be arctangent of y, and then square root 1 plus 1 over 1 plus y squared, all squared there, dy. And there we go. Both of those would be equivalent expressions for the surface area of that shape there. So, why did we go through and do all 18 of these integrals? Well, for a couple reasons. One of the major things that we've sort of seen throughout this course is learning how to use the definite integral to understand geometric constructs. So now you know how to measure lengths using definite integrals. That's arc length. You know how to measure areas using definite integrals. You know how to measure volumes of three-dimensional solids using integrals, and surface areas of three-dimensional solids using integrals. So pretty much every geometric construct that you guys have encountered beforehand, either in geometry classes or wherever, you can understand from a calculus-based perspective. Also, since we are getting nearer the end of our course, it's a good idea to start reviewing some of the earlier stuff. So while some of these examples were the Chapter 8 material, like arc length and surface area, some of them also went back to Chapter 6 material, like the area under a curve or the volume of a solid of revolution. In our next video, we'll wrap up section 8.2 with sort of a very special sort of discussion involving infinite shapes.